Let's talk briefly about some key terminology related to power and polynomial functions. One of the first functions that we're going to study in this course are polynomial functions. And as a matter of fact, you are already familiar with a bunch of examples of polynomial functions. You've seen straight lines that were literally just either a horizontal line or a vertical line. That would be like y is equal to some kind of number. In grade 9, you were introduced to the beautiful linear functions that took the form y equals mx plus b. And then we sort of expanded your world and you saw quadratic functions, both that opened up. Ooh. And that opened down. That look like y equals x squared, or even we could add a leading coefficient here. And you also should have seen cubic functions that look like this kind of an S shape. And cubic functions take the form y is x cubed. They might look like that, or they might go backwards. There we go. A polynomial function that we've seen, a polynomial function takes this form where we are going to write out our f of x is a n x to the power of n plus a n minus 1 x to the power of n minus 1, and this keeps going until eventually we land at a1 x1 plus a0. Excuse me. N is going to be any whole number. Okay, so anytime you see an n here, it's going to be related to any whole number. A is going to be the coefficient, okay, of any real number here. And then last but not least, another key piece of terminology here is the degree. And recall the degree of this function is just going to be the largest exponent. So in this case, it's going to be n. We write it this way, this is quote-unquote the simplified version of it, because the powers on our variables, the powers on our x's are decreasing. So if this was a degree 10, then this would be a 10, 10 minus 1 would be 9, and then we'd have an 8, 7, 6, 5, 4, 3, 2, 1, and then subsequently 0, okay? Basically, this is a really fancy way of writing a polynomial function. A power function, on the other hand, is just a simpler version of a polynomial function that looks like this. It's just one term. Polynomial functions have lots of terms. Power functions just have one. So an example of a power function would be something like y is 6x cubed. Versus a polynomial function would be like y is 6x cubed, but then take away 7x squared, and then maybe plus 1 over 2x, take away 10. Lots more terms. A power function just has one. Okay? Just to do a sort of minds on a warm up here, there's a lot of different ways that we can describe functions. I've got 4 different examples of functions here. Don't worry if you're freaking out at looking at some of them, because we're going to get there. Focus primarily on the descriptors. One descriptor that comes to mind for me, or two I should say, are the intercepts. So we could say, well, what is the number of intercepts they have? And then their location. So you can see, for example, like on our second polynomial here, he's got only 2 x-intercepts, whereas the third one there's got 3 x-intercepts. Let me actually highlight these so we can see better. Our second one's only got 1 right at the bottom there, and same with the first one. We also can have our number of y-intercepts. And then the location. There should only be 1 y-intercept in order for this to qualify as a function. In this case, for the first two, the y-intercept is the exact same location as the x-intercept. And for the second two, we've got a y-intercept here and then here. We might want to talk about the domain and range of our functions. We can use that to describe them. We're also going to start talking about what's called a turning point. And a turning point literally is sort of where the graph turns around, where the graph changes direction. And again, we could be talking about the number of turning points, just like we could be talking about the location of the turning points. Let's look at a couple of examples here. So I'll highlight our turning points in yellow. Let's look at our last graph. Our last graph has 3. It's got 1 at the top here, 1 sort of midway, and then we've got another one, and then the graph goes on forever down to the right. Our third graph has 2. We've got this peak here and then this valley. Our second graph, right at the bottom here, there's another one where the graph literally turns around. Our first graph actually doesn't have any, because at no point in time does it ever actually turn around and do a 180. It just continues on. We might also be familiar with the term vertex. And the difference between a vertex and a turning point is simply that a vertex is the sort of bottommost or topmost point on your graph. You saw those with quadratics, so I'll use our second graph as an example here. It's got a vertex at the bottom, but it's the only one with a vertex. Nobody else has a vertex. They all just have turning points. And then last but not least, we're also going to begin working with what's called end behavior. End behavior tells us how does the graph extend towards infinity. I should say how and where. Okay, what we're asking ourselves is as it goes to the left and as it goes to the right. Okay, so let's do our third graph as an example. Our third graph, on the left-hand side of the graph, my graph is going down towards negative infinity. So on the left-hand side, I would actually write x approaches negative infinity. I'll add a little purple arrow there so we can see that it's going all the way down. And then on the right-hand side of my graph, it's actually going up towards infinity forever and ever and ever, and that's going towards positive infinity. So on the right-hand side of my graph, it's going up. What this helps us to determine is the quadrant locations of our graph, and we'll get into that in the next video. Because you know which quadrant or sort of where the graph is going on to infinity towards. Okay, in this case, x is going towards negative infinity on the left, which means that my left quadrant on the left-hand side of my graph, it's going down. And so my graph would be starting in a negative quadrant. It'd be starting in quadrant 3. The right-hand side of my graph's going up to positive infinity up here. That's going to be in quadrant 2. Basically, the end behavior helps to tell us which quadrants our graph is going to be ending in, and that's useful for sketching, which we're going to get to in the next video. Okay, just some basic definitions here, not a lot that you need to totally memorize.